All right, welcome to the second class, everyone. I want to apologize for faulty videos that I uploaded. The mic misbehaved, so you have only the beginnings of the previous videos that has sound, and later the sound switched off. So that's why it's good to come to the class, but I will do my best that the future videos would have sound throughout the full length. My question is, do you guys see my posts and like the lecture that I uploaded? Because I'm still fighting with Canvas. You know, you have to put a lot of green ticks and publish and this and that, and still not everyone sees it. So if you can't find something, just write me an email. So somebody wrote it to me, so that's why we figured out that this was not visible, and we'll put it online. And one more thing, I want to encourage you, form the groups. So now under people in Canvas, Cesar prepared the number of groups that you can join and form, and you can see those that already have some members. You can contact them and discuss how you proceed. But I want at the end of this week all groups to be formed, and they can select papers and start working together, because this class will be also group work. This is we want to encourage some collaboration. Okay, so now then we can start with the basics, that sort of to have the common language and the common notations that we'll use throughout the course. And I believe maybe for some of you will be easy. Maybe that's the point. But just bear with me. Maybe you'll find some interesting bits and pieces throughout the lecture that will not make fall asleep. I guess all of you had some kind of courses where you dealt with graphs, right? So this will be the recap. A graph is a way of specifying some relationships among the objects, and of course we'll have vertices and edges, and the two nodes will be neighbors if they are connected by an edge. That's self-evident, and usually, I mean, this almost in every single paper or notation, n will be the total number of edges that you will see in the graph, and e will denote the total number of n will be the total number of vertices or nodes, and e will be the total number of edges that you will have in the graph. And we'll say the graph G will denote G and E, where we'll say that we have a graph with n vertices and e nodes. So that's super easy. Now we can start complicating things. So some graphs might have edges that have directions. So for example, these are two similar graphs, but this graph now suddenly has some directionality or orientation, and we might want to do that when we represent certain type of systems. So can you give me an example? What would be a, say, real-world network that we represent in an undirected and directed way? Yes?
Twitter versus Facebook.
Very good. So that's exactly the point, because in Facebook you cannot create a friendship if your edge is a friendship unless both parties agree. So sort of you have to have a bidirectional or undirected, in a sense, edge, while Twitter, you can do unilaterally. I just follow you and you have no even idea that I exist. So that would be like Facebook graph or collaboration graphs, where it involves both parties to be involved on an edge, while say Twitter or phone calls, where even though both parties are involved but there is a directionality, I call you and you are a receiver of the call, then you can put the direction on the edge. Also citations, and in some cases they also have a directional graphs has a time perspective, because for example citations, you cannot cite a paper that will be published in the future, right? So for example, this graph might not have resulted from citation graph, because if this paper cited this paper and this paper cited this and that cited back again, so there is something wrong with the timing here. Okay, So just to sort of give further perspectives of what directionality can bring and why it actually arises. Now, furthermore, we can now complicate things even further. The graphs can have edges that some are sort of better than others, or fatter, or we say have a different weight. So again, in this graph now we say that this edge has a weight 5 while this has a weight 1. And again, what could be an example of real-world system where we might want to use edge weights?
Routing.
Sorry?
Routing, the fastest path.
Yeah, so for example, if it is some kind of communication network, there could be, you can indicate a throughput or delay or some other goodness of the pipe that would decide you to go maybe one way, not the other. Okay. Or you could be, even in social networks, you could say this B is 5 times better friend with D than with C because maybe it exchanges 5 messages a day than 1 message a day. I mean, so you can start indicating the sort of what happens on the edge and the quality of the edge through the weight. So all of this I would like you to sort of start thinking for your project, what would be my data set that I would transform onto the graph, and whether it will be directed or indirected, what would weights mean, and so on. So sort of you can start in the back of your heads, doing sort of these mental thoughts. So yeah, so we could represent with edge weights, say, distance, cost, frequency, etc. Now, one of the sort of it's not the most, but very important measure on the graph is basically a node degree. So a graph, we say that every node has its own set of neighbors, and that we usually denote it as k. It's also not always, but very often, as you will see, whatever is k is basically the number of neighbors for a specific node. So we say that node ki, or ka in this case, if this is our node A, would have 4 neighbors because it has 4 edges outgoing from its own. Now tell me, what would be the average degree of the whole network? How would we calculate that? If we now know that ki is the number of individual nodes degree, what would be the, yes?
Isn't it edges divided by vertices?
Yeah, but we can only now go through the k. So say you sum up maybe all ki's, you go through every node. So what would be the average degree then? If you sum up all the ki's, what would you get? Yes?
Divided by the number of nodes in the graph.
Yeah, then you sort of normalize. Do you need something to do one more thing?
You divide by 2 because everything will be current by.
Yeah, so and then you need to divide by 2 because if you sum up all the ki's, that means you counted every edge twice. Because if I sum up ka in this case, so I've counted that edge, that edge, that, and that edge, but when I will arrive to that node, I will again count the same edge. So every edge is counted twice. So if you want to know the total number of edges, you sum up all ki's, divide by 2, and if you want to find the average degree, then you also divide by n. Okay, so we sum up for every node its degree. We make an, we divide, we basically then will get 2e, basically is 2, that means we counted twice the number of edges, and the average degree we just divide by n, okay? In directed networks it's very similar. Now just suddenly things are a little bit different. It's because we have a different sort of types of degrees. We have in degree and out degree. Okay, and the question is, can you have in some graphs the sum of in degrees is lower than sum of out degrees? No, because every edge has a beginning and end, and you should be consistent. So if you have for every beginning, you should have also an end. So in a sense, the sum of in degrees should be the same as sum of out degrees, and then the sum of the average number of say in degree would be e divided by n. So not 2e, but just e divided by n. And then we also have a notation of source node where it doesn't have any in degree, so it just spit things out, nothing incoming. And also we can have a sink node where just going the nodes are going, the edges are going in, so nothing is going out. Now another notation, dense and sparse graphs. So what do you think? What is a dense graph and what is a sparse graph?
Sparse has no many connections between nodes.
Yeah, so it's a very vague description, but we will see it very often in the real networks. That real networks are sparse because most of the edges that could appear are not present. So meaning that, remember we discussed in what is the all possible number of edges that could exist in a graph of a size n? Remember when we calculated. So if you have n vertices, how many edges could there be?
N times n minus 1 divided by 2.
Yeah, so this is for undirected case. It's basically n times n minus 1 divided by 2, or very roughly n square, order of n square. I mean, so that's what you would sort of expect if you fill. This is probably a complete graph where all the edges are present. So it's every neighbor is neighbor to every other node. And that's order of n square nodes, but that's not what we find in real world networks. Because real world networks very often have a sort of phenomena that are not scalable to produce order of n neighbors for every node. We simply say in social networks maybe we don't have much time in our 24 hours to maintain 6 billion friends, so you just have a pretty limited amount to maintain, say 200 or 300 friends in our lives. So that's why there is a cap on the number of friends for a social graph. Similarly, maybe there is a cap for a number of road intersections, roads that come into intersection just physically. I mean, in the other cases, you take any network that you can imagine, and usually the phenomena how you form neighbors has a sort of a capacity limit that you would not be able to connect to every single sort of or majority of nodes in the network. The only networks that we have, dense are sort of synthetic networks that we generate ourselves. Let's say if we decide to compare every single pair by some similarity function, then we can produce a dense graph. But what I would like to tell you that we should be afraid of dense graphs, because all the algorithms we're going to see in the course will probably have to touch an edge at least once if you want to extract something. So if you have a dense graph, you'll have to touch order of n square edges, maybe multiple times, and that will basically break your algorithm. So whenever you're going to extract whatever the graph from your data sets, make sure that it is sparse. Okay. So basically the notation will be that dense graph has a number of edges that is close to the maximal number of edges. And we just discussed that maximum number of edges is the order of n square. And if a graph has actually all possible edges, or Emax, we call it a complete graph. So that is a complete graph here. And then the sparse graph, again, I didn't want to give you a precise notation what is a sparse graph, but basically a sparse graph would be that on average, every node, say, has a quite either constant or, let's say, a number of neighbors that grow logarithmically with the size of the network. So the overall number of edges would be, let's say, order of n log n. And then we would say it's a sparse graph. Okay. And then these are examples of real-world networks. So for example, internet, which basically nodes are routers, links are internet connections. It's undirected graph. And we have, I know in this specific data set, 192,000 nodes, 600,000 links. So average degree is 6. So you see it's pretty low, pretty sparse, because although you have hundreds of 200,000 nodes, every node has only on average 6 links. And similarly, if you take any other real-world network, which is here, let's say, email or actor or citation or some kind of E. coli metabolism network where nodes are metabolites and links are chemical reactions, you always see that the number of neighbors is quite low. It's because of that that the real-world phenomena that drives the formation of the graph has a scalability issues. So you cannot just be connected to everyone. Do you have a question?
So is there an example of something that is like a dense graph, like we might theoretically encounter?
So as I said before, some sort of the pitfalls are the following. Say you want to calculate some kind of a goodness measure, so some similarity measure between every node in the graph. Let's say you want to make some recommender system and you say, I will now produce for every node or a person some kind of vector that, say takes into account my hobbies, my location, where I live, what my, say the profile is, what university I finished, And let's say you find some kind of a cool distance function telling that I could compare any two people. And if they are from the same region and from the same university and from whatever the same age group, I would think they are of the same type and I will recommend them the same, say, movies or the same products. But then you say, then I will compare every single person that I know, and then you produce a fully connected graph where an edge would be your calculation of that you developed a similarity function, a goodness function, and then on that you want to maybe run some algorithm that will produce you some recommender system. And that would make it a dense graph, because you artificially forced every edge to appear. And that could be valid in certain cases, but it's very likely that you will end up in a situation where it will be just not scalable to process. And then you will maybe start thinking, maybe I should actually prune the graph, because maybe majority of my similarity function values would give me something close to 0, because most of the people may be dissimilar, only some of them are similar. And then if you do the post-processing of that dense graph, then you will find out that if you sort of ignore some values after some threshold, then again you will end up with a sparse graph that still contains your information. The similarity function that you discovered, is still present, just it's sort of zeros, not very important pairs. And then on that graph, you'll probably be able to scalably, run your algorithm and discover something interesting. But usually it is synthetic graphs that happen to be dense. Real-world graphs that you extract from real-world systems, I mean, it's very unlikely you will have anything dense, pure to the fact that an object in real world has to interact with the world, and it's unscalable to interact with everything. So that's why it's sparse. Any other comments, questions? Actually, I appreciate that you ask questions and we can discuss it and be more interactive. Okay. So this is just a first glimpse that the real world is sparse, okay, and it's good for us. Then we are way more scalable than, not like in the previous class where we would need to brute force every possible situation, if everything is dense. So here we can still have some chance to, to run interesting algorithm and achieve the final result. Now, there are other type of graphs which is called bipartite. Maybe somebody already heard about that. Do you know, can you guess what a bipartite graph is? Sorry? So up to now we were saying that a graph contains of nodes that are some kind of objects from real life and they have some relationships. But we sort of implicitly assume that these objects are homogeneous. So say just, object is a profile in Facebook, so everyone is a profile. It's, everyone is of the same sort of type or kind. But often you have system that has several types of objects. So for example, products and user, or let's say movies and users, on watchers, or for Netflix case, or in Amazon, the buyers and products. So suddenly the object has two kinds of different things, and if a user watched a movie or a user bought a product, then there is a relationship between these two different objects, but they're of different kind. And in this case, we form graphs that in a sense have, they're usually represented in different colors of nodes. So say we have black nodes and red nodes. So say movies and people who watched, and there is a link if they watched a movie. And in this type of graph, we do not permit links between the same kind of group of nodes. So the links can only go from one to the other, but not within. Okay. So basically, more formally, bipartite graph is a graph whose vertices can be divided into two disjoint sets U and V. So say for two different types of nodes, such that every edge connects a vertex in U to one in V. So that's all we allow. And again, we can also say that we can have a complete graph. Bipartite graph is all the vertices are connected. Every vertex from one side is connected to every other vertex to the other side. So this is, for example, a complete graph, a bipartite graph. Okay. And you can also extend it to tripartite or qupartite if you have several, not only two kinds, but maybe three kinds. Maybe you can have a movie and an actor and a producer, and then you can keep on continuing. So that could be a. The problem with this type of graphs is that we'll see later the behavior of say how information spreads within this network. So say we will talk about random walks. They have a different convergence behavior and criteria. Then we have to double check if they are bipartite or not, otherwise we might end up in some problematic situations. So there's other examples of complete bipartite graphs. So we already discussed the examples. So say this is authors to papers, or authors to movies, users to movies, and so on. Having bipartite graph, we can still project it to sort of our regular graph that is sort of one type. So for example, if you have a bipartite here, you could say, I would like to project this graph only to say U, which is users, for example. And I will make a link between two users if they watched the same movie. So for example, 1 and 2 has a link because they watched this movie A, or whatever was that. And there is no link between 3 and 5 because 3 and 5 do not have any common movie that they have watched. And you can similarly say connect the movies. If V is movies, say that A and B are connected movies because they had a user, at least one user who watched them. And also while projecting, you can put weights here because maybe this users 1 and 2 watched not only one movie, but maybe they watched 2 movies or 3 movies, and then you can put the weight here depending on how many movies they watched. And then suddenly, if you now start looking at this graph, these were users and movies, you could see which users are sort of a similar kind. If you watched, you and your friend, or even if it's not your friend, maybe two persons watched, 25 or 250 the same movies, that means they are of the similar interest. And maybe these people should be, say, then grouped together later on in some system and start recommending the same things. Also here you could say if these two movies or this cluster of movies are watched by the same people, so maybe they're the same kind of movies. Maybe they're all, say, science fiction. Because the science fiction related people are watching this movie. So only by, even if I don't know anything about the particular, whether this movie is a science fiction or romance or whatnot, just by looking at these projections, I can already infer how many types of movies there exist and how many types of users there exist in the world. Even if everything else is, for me, I would like to say in Chinese, because I have no idea about for me this is totally blind, because I cannot read, I cannot understand. So even if it is in Chinese, I could still figure out just by who did what to extract how many communities there are or how many types of users there are. And that's what I would like you to try to do something in your projects. So very often in other courses, you would be dealing with the content. You will try to analyze the content, to extract the knowledge from the content. Here we say you first look at the sort of metadata of the graph, and only from that you can see that you will be able to do a lot of interesting exploration, and this actionable knowledge will pop up just by looking to the networks that are produced by this phenomena. Okay, so another type of sort of thing to be careful are isomorphic graphs. So have you heard of them? Anyone? Do you think these two graphs are similar or very different?
Similar.
Maybe something stronger? These are actually exactly the same graphs. So another thing is that sometimes, and actually this graph is bipartite, Although before we saw that bipartite sort of has a clear nodes on the left and nodes on the right, but it's not a law of nature that you have to always draw it that way. You can draw as you like. And although here we can see that this graph is bipartite because we can visually inspect that this is a set of nodes do not have any connections on the left side, and then the set of nodes do not have any connections within each other on the right side. It's bipartite. But if you redraw it, and if you know a mapping such that every node here is mapped to every node there in such a way that if there is a link between, say, blue and green node, you will find in both cases, and if there is no link, you also will not find in both cases, then these graphs are isomorphic. So you should be very careful, in a sense, in how you interpret the graph. So in the first sort of look, it might be either, say, not bipartite or might not have clusters, but just the way that you drew it. And you can, the graphs are sort of, unless they are embedded in some coordinate space that you cannot, change the location of actual nodes, usually you can draw as you like, and therefore, or you can rename the node IDs in a sense, because in that case maybe this is the A and this is 1, but as long as there is a structure that, and you can have a mapping between these, or find a mapping between the say, a node in one graph and the other graph such that the connectivity is preserved and exactly the same, then these graphs will be isomorphic. Now we come to the sort of, probably you will see it very often now in this and future courses, how to represent the graphs. and I will try my one of the goals of this course is to convince that every graph is a matrix and every matrix is a graph. And graph operations are matrix operations. Okay, so usually what you will see that a graph is represented by adjacency matrix, where adjacency matrix has a size, is a square matrix of a size of n, where n is the number of nodes as we discussed. And if you see, and in the cells will have values, say in the simple case, zeros and ones. You will put 1 if there is an edge from I to j. So a cell aij will have 1 if there is a link from node I to node j, and if it will be 0 if it is otherwise. Okay, so for example, this graph results in this adjacency matrix. And this graph, which is directed graph, results to slightly bit that other adjacency matrix. So tell me, when are the matrices symmetric? Yeah, okay. So this is this a symmetric matrix? Yes. And this? No. So in which case is there a symmetric and which not?
Undirected and directed.
Yeah, so whenever you have a undirected graph, it will always be symmetric because aij will, if aij is 1, then aji will have to be 1, right? So you will always, in an undirected case, will see symmetric matrices. And for many algorithms, this is a sort of a blessing, because otherwise it sometimes breaks down. So we like undirected matrices. But as we know, certain systems cannot be represented in undirected case, so we have to have directionality. And there you will have a non-symmetric matrices. Because if they somehow become symmetric, that means the directed links have, you know, both directions, and then you can treat it as undirected. So how to find a node degree using additional matrix? Like if you look at this, what's the node degree? How do you, node degree of node I?
Check the diagonal.
No, diagonal would mean, in a sense, II or A11, A22 is to your. This is the relationship to yourself. If there was a loop here, it would be 1. But in a generic case, we don't permit loops. So to find out a degree, you can just sum up a row or a column. In a symmetric matrix, it's the same, right? So if I want to know the degree of the node 2, I just sum up everything I see, and I'll find that it's 2. And you can double check, yes, it's 2. And in the indirected case, it would a row would represent, say, out degree, and the column would represent in degree. Okay. Now, how would you represent weighted graphs in matrices?
So 1 will be 2, 3.
Yeah. So if you now have some edges are better than others, then you will find some kind of different numbers here. And how would the adjacency matrices of real-world graphs look like? So it will be huge, first of all. Like, you know, if you talk about social networks, will be, you know, the millions and maybe billions if you are on Facebook. But the content will be mostly zeros because of what we discussed before. If you want to represent, I'm not sure people do represent, for sure not, but if you would represent Facebook graph, how many Facebook now use? I don't know, 2 billion? So 2 billion times 2 billion. And on average, it's probably, there's even a cap on the number of friends you can have. I think it's some 5,000 or something, not to become some kind of bot. So a row, say, of 2 billion, and only out of 2 billion, say, a few hundred ones. So most of the things are empty, Okay, so now that's again, and usually in real life you don't really, for that reason, do not operate with the matrices, but this is more for since this is more algorithmic course, we will try to put our brains into linear algebra point of view. We'll see how the algorithms work. But in real life, you sometimes will be afraid to put everything into matrix because it's mostly zeros, and the matrix operations will be, too expensive for you to do it on the very large graphs. Okay, so we discussed here that unweighted and weighted. So if there are weighted graphs, you will find some kind of different numbers here. But and then if you want to calculate, say, the number of edges, in the unweighted case, you just sum up all the ones you see, and then basically you count every edge twice, so it will be 2e. And if you want to find the average degree, you just divide by n. And in unweighted case, you cannot really say that there's a number of edges anymore. You usually say this is what's the total weight of the graph, and you can also discuss what is an average weight per node, sort of similar to average degree, which would be of a similar kind. So now in this case, e would be not the number of edges, but basically the total edge weight in the network. We also discussed what happens if you have loops. Here you see, so sometimes the loops are allowed, and again depending on which type of network you are processing, and if loops are there, then suddenly something appears on diagonal. Because loops mean some kind of relationship to yourself. That means it's if you are node I, that means the node is an II cell, some kind of behavior. And similarly to weighted graph, you can have multigraphs where you would sort of allow several edges going from the same two objects. So this would be equivalent to weights. So you could say that maybe this guy sent 3 messages from node 2 to node 4. So either you can represent it that way, or you can just say it's a weight 3. So it will be, from the matrix perspective, you would not see a difference. Okay. And this is an example of some kind of maybe real world adjacency matrix. So you see this is already, it's not billions, but now quite a lot of nodes. And whenever there is a link, we put a dot. So you see it's mostly empty. Okay. But already looking at this, can you say something? Can you say which is maybe the most important node here or something? What do you think?
The lines.
Yeah, so you see there are lines. And what does it mean, a line? Yeah, that person, node whatever, 255, for some reason has a lot of neighbors. So it's if you now draw it as a graph, it will be a hub. Maybe it's some kind of Barack Obama, I don't know, or maybe in social network could be some kind of a bot that just keep on a spammer. So again, depending on the problem you have, this could be a maybe an anomaly that you would like to get rid of. Do you think it's directed graph or indirected? Yes.
Directed, because you see, isn't there like 2 lines that way, but only 1?
Yeah, exactly. So you see, this if only this would be, it seems to be like asymmetric, but that one you don't see it here. So I mean, again, this is almost, how to say, anecdotal, but you could see that it's no symmetry here. That means it's probably undirected graph. Good. So one way to represent this basically graphs is matrices, and again, for all practical purposes for us, we will use matrices in our heads, and we will do lots of algorithms with matrices. However, they are not sort of very efficient in real world. So another way to represent would be, in a very efficient way, just to have a, say, edge list. So you have a graph and you say there is an edge 2 to 3, 2 to 4, 3 to 2, blah, blah, blah. You put all of them. So it's a very efficient way to represent, especially if the graph is sparse. And we say that most of the graphs are sparse. But now you will end up in problem on how to find a specific edge. Usually then you have to traverse all the graph just to find all the edge list to find the specific edge you want. So that's also not a preferred way to to store the graph. So usually, when we have these large and sparse graphs that we observe in the nature, let's say we use the adjacency list. So meaning there is some kind of a hash table that we store the nodes, so we can very efficiently find the node, and then there is a list or a vector for every node that that indicates what are their neighbors. And you can also have for indirected graph both in degree and out degree. So this is for, to make things actually work. But this course is not about, the sort of efficiency. For that, you need to take another course, ID2211, where they do talk about the graphs and how to efficiently store them, and depending on what kind of algorithm you run, how to process it. But for us, all of our sort of mind will be in matrices. Okay. So just to finish up with edges, so the other attributes that edges could have, so not only weight, we can also have, for example, ranking. Sort of best friend, second best friend in the social graph, or say type can be friend, relative, co-worker, capital of, husband of, all this. You could also have a sign, for example, trust, distrust, friend or foe. And actually there was some also paper, I think it's published. For example, you can explore trust and distrust networks. So here there are two types of edges, like green and red, which probably denotes either trust or distrust, or friend and foe. And you can see how things evolve there and what kind of structure you see. Is it that the sort of, if you see a triangle and if you have two edges red, is enemy of my enemy my friend? How this propagates. So you can already also find very interesting problems to solve if you have this, not only the simple weight, but also the sign of the network. So again, to recap, for example, email network would give us a directed multigraph with self edges, because apparently you can't send an email to yourself. I guess it's not disallowed by the email protocol. Facebook friendships will be undirected and unweighted. So there are no self loops and there are no directionality, because Facebook, Mark Zuckerberg doesn't allow to befriend yourself. And then citation networks, unweighted, directed, and acyclic. Remember we discussed. So there are no cycles, because you cannot cite, then you would destroy the timeline of the phenomenon of citations. Or collaboration network is undirected multigraph or weighted graph, depending how you want to interpret. Depending if you collaborate a lot, you can have either many edges for every collaboration event, or bigger weight if you want to sort of collapse it. And the same with mobile phone call graph, protein interaction, so you name it. So that's sort of for you, like for homework, to figure out what is your data set and in what type of graph it will result. So maybe we can start, before I let you for a break, with the main concepts within the graph, and we will cover path, cycles, connectivity, components, and distance, and maybe a bit more if we have time. Do you know what is this graph? Maybe by just looking at the IDs.
Universities?
Yeah, some of them are universities, but this is a very famous graph actually. Yeah, this is the first instance of the internet, like in the 60s, 70s, when DARPA, made a project that they connected the East Coast with the West Coast of the United States. So here you could see Harvard, Carnegie Mellon, MIT, and then on the east side and on the west side there is University of California, Santa Barbara, Los Angeles, Stanford, Utah. And this is the first sort of piping of the internet. And now we can use it as an example. So we basically, the first concept would be a path. So we say a path is a sequence of nodes with the property that each consecutive pair is in the sequence is connected by an edge. So for example, this could be a path. And later, for our algorithm, we will use the term random walk. And random walk could have taken this type of path. Okay? We could say a simple path is a path where the nodes do not repeat. So for example, this is a simple path, while the green one was not simple because it hit twice UCLA. So, and sometimes we can be referred to walks and paths. So walk is the one that you can hit things several times, and path is where you can only hit a node once. So now tell me, what would be a distance in a graph? How would you say, what's the distance between B and D?
How many nodes between?
Yeah, so but how many nodes between B and D?
The number of nodes in the path?
The number of nodes in the path. Okay, so B and D would be how many then? 1 or 2? Because you could have a path like this.
The smallest path?
So the max.
So the min maybe. The min, okay? So actually what we say that distance is the shortest path between any pair of nodes. Okay, and we actually count not the nodes but the edges. So from if you go from B to D, so there are 2 ways to go, either BCD or BACD. And if you count edges, so in one case it will be 2, in another case it will be 3, and we take the shortest, it will be 2. Okay? So that's how we define the distance. And sometimes a graph can have a disconnected node. So the distance here we would say, well, that's unfortunate, it's infinity. Okay? And in directed graphs, it's similar, just that you can walk only in one direction. So, and the result is that sometimes the distances are not symmetric. So from, say, from A to C, if you want to go from A to C, you have to go A, B, C, so it's 2. But from C to A is only 1. So the distance is not symmetric, while here is always symmetric. Okay. Okay, let's take a break for 10 minutes or so, and then we continue.